Okay, so I guess that in this crowd, I don't have to convince you that distributions are everywhere. Sort of, we, our colleagues, and even a lot of other people are constantly trying to understand what. I think distributions are everywhere is something we can all agree on. And in fact, many of us, our colleagues and lots of other people, are constantly trying to understand what sorts of properties these various unknown distributions might have. And what sorts of properties might be interested in? Well, if you want to play the lottery, you might be interested in knowing a couple of things. Maybe you'd want to know, are the samples really coming from the uniform distribution? This could be good and it could be bad. For example, my student Krzysztof, who's in here somewhere, pointed me to a story from Poland where there was a lottery that gave some of the balls had more probability than others, and when people figured this out, they made a lot of money. So it's actually sometimes good to know that your lottery is not uniformly distributed. But you might also want to know, are the draws independent? If you're interested in looking at people's shopping patterns, you might want to see whether sort of shopping patterns are independent of zip code. You might want to compare transactions of 20 to 30-year-olds, 30 to 40-year-olds, and see is there some sort of a trend change, or in other words, are these distributions the same, or are they far apart, say in something like L1 distance? You might want to ask about similar properties about disease data, but you might also be interested in the shape of the distribution. You may want to know, are the diseases more prevalent near big airports? Okay? Or is it monotone decreasing with distance from the airport? Another property of distributions that people really care about is entropy. For example, these people were interested in the entropy of a signal because it told them which neurons respond to which stimuli. So what they did is they apply the stimuli to the neuron. They get some kind of signal that looks like that. Okay? And then they do this many times, and they take the entropy of the description of this signal. Okay? And that gave them some idea of whether the neuron was responding to the stimuli or whether it was just background noise. Okay? So that was another place where you might be interested in distributions is if you have huge data where you don't have time to look at all the data, you just have time to sample it, but you want to have some idea of how compressible is this data. So how compressible in general is undecidable, but how compressible via, say, Huffman codes would be just estimating the entropy from samples of the data. Estimating how compressible it is via Lempel-Ziv is essentially the problem of figuring out how many distinct items you have in your data. So there are also distribution questions hiding in there. Okay, so in all of these examples, what we're interested in this talk is global properties. I don't have a formal definition of a global property, but essentially these are properties that are robust under small changes in L1 distance of your distribution. Okay, so for example, I take my distribution and I say it's close to uniform, and then I slightly change my distribution in L1 distance. It's still close to uniform. Okay, it's a little bit less close, but it's still close. So what's not a global property is I'm not interested in properties of, say, just a few of the elements. Like I'm not going to be interested today in properties that ask whether there is an element of weight at least 1 over square root n or something like that, because it's just a small local part of the distribution, and it changes a lot when you change the L1 distance. Okay, in all of these cases, we're going to assume today that all you have access to are samples of the distribution. You do not know anything else about the distribution. And we're also focusing on the case of large domains. Okay, so in all of these examples we had before, there are lots of different types of answers, outcomes from the probability distribution. And the reason is that basically the standard techniques are just fine for small domains. Okay? But we're interested in large domains because for large domains, most of the techniques require a linear number of samples in the size of the domain. And what we're interested in is if you can find techniques with sample complexity that's sublinear in the size of the domain. Okay? And this is a place where you cannot use the standard statistical techniques like chi-square tests or learning the distributions and arguing about using Chernoff bounds or Houghton bounds that you have a good approximation of your distribution. So you need something else. Okay? Here's our model. We're assuming the distribution is given by a black box. It's a purple box here. The distribution we're assuming is over a discrete domain. The domain size we're going to denote by little n. Okay? And let's just assume for now that the elements are labeled 1 through little n. And this box generates IID samples. Every time you push a button, you get a new sample. We're going to use p sub I to denote the probability that p outputs I. But these p sub I, let me stress, we don't know these. This is just what we're going to use to denote it in the talk. But we don't actually know the p sub I. And of course, we're interested in the sample complexity in terms of n, little n, the domain size. Okay, so let me just give a brief overview of some of some things that are known, and then later I'll focus on shape properties. The first kind of question that you might ask about a distribution is whether it's the uniform distribution. And it turns out that the sample complexity of distinguishing uniform distributions from those distributions that are far in L1 distance, epsilon far in L1 distance, is theta of root n. Okay? So you need root n samples to distinguish uniform from far from uniform. And just occurred to me that I haven't defined L1 distance, so let me just define that for a second. So the L1 distance between P and Q is summation of the absolute value of P sub I minus Q sub I. Okay, so we're just summing all those little differences. So testing uniform distribution from far from uniform distribution is theta of root n. Okay, that's very interesting. Okay. All right, I'm going to say a few words about how to do this because that turns out to be a very important problem even for the rest of this talk. So the one way to do this, and this is actually not the best way to do it, but it's the way I'm going to talk about in this talk, is to just estimate the collision probability of your distribution and make sure that it looks right. Okay, what does look right mean? Uniform distribution should have collision probability 1 over n. So if this distribution that's in your black box has collision probability that's much greater than 1 over n, then it shouldn't be close to uniform. Okay? So we're going to estimate the collision probability, make sure it's something like 1 over n. And the other thing we need to do is bound the infinity norm, which means that's just the make sure that there are no elements whose probability is more than, it turns out to be 1 in square root n. Okay, so we're going to make sure there's no really heavy elements that occurs too often. Okay, because that should not happen in the uniform distribution. So that's the whole test. The only difficulty is the collision probability of the uniform distribution is 1 over n, so do you need linear and n samples to estimate that thing well? Like, to see if the collision probability really is 1 in n, you might think, oh my, you need linear and n many samples to estimate this very well. But it turns out, Goldreich and Rahn noted that actually, if you take k samples, you have k choose 2 pairs. Okay, and you can use all k choose 2 pairs to get a good estimate of your collision probability. And even though those k choose 2 pairs aren't independent from each other, they're independent enough so that they give you a really good estimator of your collision probability. So actually, root n samples gives you a really good sample to within very close to 1 in n of the collision probability. And that's why root n samples is enough. And that actually alone gives you a really good estimate of the L2 distance from uniform. And when you also bound the L infinity norm, you can further make claims about the distance in L1 from uniform. Okay, so this is all you need to do. I should mention that the algorithm I just sort of described from above, essentially the only thing you need to remember here is we're going to estimate uniformity via collisions, pretty much. I should mention there's a different estimator due to Paninsky that gets rid of a log n factor and gets the optimal answer. And he actually looks at a different statistic. He looks at the number of elements that occurred exactly once. But I'm not going to go into that any more than that, just to say that there are other ways to do this. Okay, Also, it's easy to see that uniformity testing requires root-n examples. Why is that? Well, let's let distribution Q be generated as follows. Pick a random subset of half the elements, okay? And then let Q be the uniform distribution on that random set of elements. Okay? It's very far from uniform because it's only on half the elements. All right, but how can you tell Q from the uniform distribution just from samples? Well, you start taking samples of Q, and you see these labels of elements, and you can't say anything just by seeing names of elements because you picked Q randomly anyway. So this is going to look just like samples from the uniform distribution for a while. And the only time you're going to see a difference is when you start seeing collisions. In Q, you're going to start seeing collisions sooner than in P. Okay? The only thing you can use to distinguish the two is the collision statistics. Okay, so this is something you can formalize, but that's the essential idea. And because in Q you don't see any collisions until root-n samples, that's the first time you can even begin to think about distinguishing Q from uniform. Okay? That can be formalized almost exactly the way I said it. Okay, so easy lower bound. All right, so uniformity testing we can do in theta of n to the 1/2, and we can get nearly the same complexity for testing if P is any other known distribution. So now suppose I have some distribution, let's call it Q again, but it's a different distribution. Q is now some distribution, any arbitrary distribution, but I've written it down. You don't need to take samples from Q. It's written down for you completely. Okay? Then it turns out that you can distinguish the case where P equals Q from the case where P is far from Q, also in O tilde of n to the 1/2 samples. So something like n polylog n. And we call that problem testing identity. Sometimes it's called testing against a known distribution as well. It clearly needs at least as many samples as uniformity. It needs at least root-n. But the fact that it needs not much more than uniformity is because that essentially there's a reduction from this testing identity problem to something like logarithmically many testing uniformity problems. Okay? So I'm not going to say any more about that right now, but this uniformity testing problem is a very important tool. Okay, here's a new problem. Here we're testing whether P and Q are identical from the case where P and Q are far. Now here, Q is not written down for us. All we have is access to samples. So I'm going to take a guess. Take a guess. What do you think is the sample complexity of distinguishing P equals Q from P far from Q? Who thinks root-n? You guys are smart. Okay. In fact, it's theta tilde of n to the 2/3. So in fact, for a while, we had this algorithm that worked in n to the 2/3, and we kept trying to improve it. We couldn't understand why we couldn't improve it. And it turned out that there was a lower bound. Okay. So some of us were kind of shocked about this, but we had to move on. Okay, what about approximating the distance between two distributions? I want to say, I know P is not equal to Q. I want to know whether P and Q are close from the case that P and Q are far. I want maybe to separate P and Q have distance at most epsilon, versus the case where P and Q have distance more than 2 epsilon. Or even, I would even settle for this. Let's distinguish the case where P and Q have distance at most epsilon from the case where P and Q have distance 1 minus epsilon. Okay? What do you think? N to the 1/2, n to the 2/3? How about n to the 2/3? Anybody going to vote for that? Oh man, you good? You're good. So in fact, this requires nearly linear samples, which some of us found kind of depressing. But so okay, I guess one note of optimism would be that there is a sort of weak approximation that you still can do in n to the 2/3 time. You can distinguish the case where your two distributions are epsilon over root-n close from the case where they're epsilon far. Okay? So there is some kind of weak approximation that still can be done, but it's very weak. Okay? So, and also, I hope that in the rest of this talk I'll mention that sometimes problems can get easier if you make certain sorts of assumptions on your distributions, which hopefully are somewhat reasonable in some cases. Okay, so I'm just going to mention a bunch of other problems that have been looked at: independence, k-wise independence, almost k-wise independence, estimating the entropy and other information in theoretic quantities, estimating the support size. These are all problems that have been looked at. But for the rest of the talk, what I'd like to talk about are testing properties of shape. Okay, so some kind of shape properties of the distribution. Again, I don't have a formal definition of shape, so I'm just going to throw some results out there. And actually, I'm really only going to talk about testing monotonicity, and then I'm going to have another slide about some other possible shapes. So I'm kind of cheating. But then that's going to be one part of the talk. And then for the last part of the talk, I'd like to assume you know something about the shape of the distribution and see how that can maybe help us test other properties of the distribution. Okay, so we're going to test properties of shape, and we're going to mainly talk about monotonicity. Okay, so we'll say that the distribution P is monotone if, okay, so first let's assume there's some kind of ordering on your domain. It can be a total order, or it can only be a partial order on your domain. Let's start with a total order. Just, the integers, 1 through 7, they're all ordered. So we'll say that P is monotone if for all pairs ij in the domain, if I is less than j in the ordering, then P sub I should be less than or equal to P sub j. Okay? If I is not comparable to j in the ordering, then I don't care about the relationship between P sub I and P sub j. But if they are comparable in the ordering, then the probability distribution should respect that. Okay? Why are we interested in monotone distributions? Well, many distributions are either monotone themselves or made up of small numbers of monotone distributions. Like bimodal distributions have an increasing part and then a decreasing part. Okay, so let's start with monotone distributions over totally ordered domains. And let's think about how we might test monotonicity of a distribution. Okay, so I don't know what the first idea that comes to your head is, but the first idea that came to my head was this should be easy because we can just pick ranges I to j and then I prime to j prime, and as long as I is less than I prime and j is less than j prime, well, the average weight here should be less than the average weight here. So I should just check that that's true on my probability distribution, and we're done. Okay? That sounds reasonable. It's like a good first step for a test. But then there's a problem. The problem is, what if you take the uniform distribution on even numbers? That's not monotone. That's very far from monotone. Okay? But that would pass any such test. Okay? That looks just like the uniform distribution if you're just looking at ranges. If you never kind of ask about specific points, it's going to look identical. So you're going to need some kind of test that distinguishes the uniform distribution on even numbers or uniform distribution on random numbers from just the plain uniform distribution. Okay? Because uniform distribution is monotone, but those guys are not monotone. Okay? So that's kind of scary. But in fact, thinking about this more makes you realize that uniformity testing is essential to monotonicity testing. So in fact, you can show that testing monotonicity requires root-n samples. Why? Because you can reduce uniformity testing to monotonicity testing. Okay? So let's take a distribution P, and let me define the reversal of P. Okay? So here's P. The reversal of P is, I'm just going to relabel the nth element as element number 1. The n minus first element is going to be element number 2. The n minus, and so on. Okay, so it's just reverse this graph and relabel. And now the claim is P is, so first of all, P is uniform if and only if P and P reversal are both monotone. Okay, that's the only way that can happen, right? Okay, well, in fact, it's also true that P is close to uniform if and only if P and P reversal are close to monotone. Okay, so the if and only if isn't actually the same in both directions, but you kind of lose something by going in the circle. But still, there's a sense in which this is true. So what it means is, if I want to test my distribution for uniformity, what I can do is test that it's monotone, and that its reversal is also monotone. And if that passes, I can then conclude that this was a uniform distribution. Okay? And I can also know that if it wasn't close to uniform, this thing would have failed. Right? So monotonicity testing is essential to uniformity testing, but maybe it's actually harder. Turns out no, because you can also reduce monotonicity testing to many uniformity testing problems. Okay, and let's see how you might do that. Okay, so the idea is we're going to try to approximate our distribution by something I'll call a k-flat distribution. What is a k-flat distribution? We're going to partition the domain into k intervals, and the conditional probability in each interval is going to be uniform. Okay, so that's what I mean by k-flat distribution. It's some kind of nicely it's a very succinct order k size description of a distribution. It's just uniform in different partitions. Okay. How are we going to... and then what we're going to do, if we have a good approximation of our distribution by a k-flat distribution, then we can just check if the k-flat distribution is close to monotone. Okay? And if this was a good approximation of the original distribution, and this guy is close to monotone, then the original distribution has to be close to monotone. Okay? So once I pass a distribution using this schema, I am pretty sure that this thing was close to monotone. So I'm not so worried about passing distributions that are far from monotone. I'm not worried about passing bad distributions. My only worry is, why should good distributions pass this thing? Okay? Why would a monotone distribution be approximable by a k-flat distribution? And for what parameters of k that are reasonable for my algorithm? Okay, so our questions are going to be, can we approximate a monotone distribution by a k-flat distribution for k polylogarithmic in n? And so is it the case that all monotone distributions can be approximated by such k-flat distributions? And secondly, is it the case that we can actually find the distribution in time root n? Okay, how do we find these interval boundaries? Okay, and that's... Okay, a final question that you might have is, how would you even check if the k-flat distribution is close to monotone? Okay, so one thing I should point out is, this is now not a sample complexity question, it's a time complexity question. In this talk, I'm not worried about time for the most part, but since here we can say something nice about time, I'm going to say something about time. Just so give me 1 minute to talk about time and complexity. Secondly, remember that k is polylogarithmic, so this is a distribution whose description length is polylogarithmic in n. Okay? So we're solving some kind of problem whose input size is already polylogarithmic. Even if you had an exponential time algorithm to solve this thing, it wouldn't be that bad. But it turns out that you can even solve a linear program on these polylogarithmically many variables and determine whether this k-flat distribution is close to monotone or not. Okay? So that happens to be something that's not a problem. But just the most important thing to emphasize here is, at this point, you don't need any more samples. Okay, so this is not a sample complexity question. All your samples are coming in trying to find these interval boundaries. Okay, so that's what we're going to focus on now. How do you find the interval boundaries, and how do you show that a k-flat distribution exists for k polylogarithmic in n for every single monotone distribution? Do I have 5 minutes left? Or do oh. How much? Oh, half an hour. Okay, great. Fantastic. Okay. Try 5. Okay. Okay. So how are we going to... Okay. So I can talk slow now. Okay. I have a lot to talk about. What do you think, Abby? He once told me I talk faster than Shafi. Okay, so we'll slow down here. All right. Okay, so how we're going to find this k-flat distribution? The idea of the algorithm is going to be, we're going to recursively partition our range into half, always in half. And we're going to stop the recursion in 2 cases. One is when the range we're looking at has such small probability that we just don't care about it. It doesn't add much error to the total result anyway. And that, so we're going to say the probability assigned to the whole range is small. In case you're interested, small in this case means something like epsilon over log cubed n. It's something smaller than that, something like that, so that all the ranges that add up with this total weight, they don't contribute much to the error. Okay? So that's one reason to stop the recursion. Another reason to stop the recursion would be that you reached a range where the collision probability is small. Okay? How small? So small that it makes it seem like the distribution conditioned on being in this partition is close to uniform. Okay? Okay, so small collision probability means at this point you must be close to uniform. And we're going to estimate this really well. We're going to use root n samples to estimate this so that we can really know that if we stopped here, you were close to uniform. Okay? If at any point in this algorithm, when we're recursively partitioning, we have too many partitions, say more than log cubed n, we're just going to stop and output that this cannot be a monotone distribution. And we're going to have to prove a key lemma that says that a monotone distribution cannot have too many partitions. So anything we fail, it's good because it wasn't monotone to begin with. Okay, when we're done, we should have k partitions, polylogarithmically many partitions, and this will be our output. We're going to have these partition boundaries, and then it's easy to sample the weights of each partition, so we can output a k-flat distribution that's close to p, okay, for this polylogarithmic k. So that's the plan. What do I need to well, what I'm going to do now is two things. I'm going to give you a couple of examples of what this recursion thing does, okay, including the stopping condition. Sometimes we're going to stop because the probability is too small. Sometimes we're going to stop because the collision probability was small and we actually had a uniform distribution in that flat. And then I'm going to show you an outline of this proof of the key lemma. Why is it that monotone distributions do not have too many partitions in this procedure? Okay, so here's example number one. Here's a probability distribution which is 1 over 2n for the first half of the elements and 3 over 2n for the second half of the elements. And we start with the full range 1 through n. And okay, so let's check why did we stop the recursion? Either because the probability assigned to this was too small. It's not too small because it's all the probability right now, so that's not going to be a reason to stop right now. Or we would stop because the collision probability was really, really low. Now in this case, it's not going to be because this thing is not close to uniform. Okay? So we're going to partition. Okay? And these are the conditional distributions you get on the two partitions. This is 1 through n over 2 and n over 2 through n. Now, should we stop now? Well, neither of them have small probability, so that's not going to be a reason to stop the recursion. But both of them have small collision probability because they're both uniform. Okay? So we stop, that's it. This is what we're going to output. We're going to output actually a 2-flat distribution. It's got 2 partitions of the data, and this is what of the domain, and this is what we're going to output. Okay? Any questions on that one? Okay, now comes the tricky one. What about this distribution where the last element gets probability 1/2, 1/4, 1/8, and so on? What would we do there? Okay, well, we definitely have bad collision probability, so we're going to partition this node. Okay, and this guy now, he has very small weight. Okay, so we're going to stop. That's just small, so we stop recursing there. On this side, however, we have large weight, and we have large collision probability. So we keep partitioning. Okay? Again, the left has small weight, the right has large weight and bad collision probability, and we keep going. Eventually, however, you start getting, actually it happened here, but I didn't use a large enough n for this example, but eventually you get to the point where you start sending some probability weight to the left. Okay? So you might not actually decide that this guy is small at some point. In fact, probably already here I shouldn't have decided it was small because it was this whole weight. Right? You can actually see it. So you might actually start partitioning on the left as well. Okay? But whatever you do, what you're going to end up with is a subset of a binary tree of height log n. Okay? So let's just think. In the previous example, we split once. We outputted a 2-flat distribution. That tree that we made was of size 3, right? Here, we have somewhat bigger partitions, right? And we end up with maybe 2 to the log n many partitions that we output, right? So that's something like logarithmic. Okay, that's good. So let's notice a couple of other things. The depth of this tree is bounded by log n, right? Because we're always cutting in half. So there's no way this depth can be higher than log n. All right, another thing to notice is either we partition into 2 or we stop. Okay, so it's actually a full tree, right? Both kids are there or no kids are there. We never have long chains. Okay, so that's another thing just to notice. Okay, because now we're going to prove that for monotone distributions, the number of the partitions has to be log n, log n. And what we're going to show is we're going to look at the tree of the partition procedure. And what we're essentially going to do is use the fact that we know there's at most log n levels. We're going to show that at any level, there's at most log n many nodes. Okay? And that's how we're going to bound the total number of partitions. Okay, so for a given level H, consider these live intervals V1 through Vm. These are the ones that haven't been declared too small. These are the ones that are still alive. They're either uniform from kind of from above, or they're still alive, but they have not been declared too small. Well, notice that in these live intervals, okay. All right, so notice that in the live, because we're only proving this claim for monotone distributions, all the probabilities in V1 are smaller than all the probabilities in V2 and so on. Right? So these probabilities are all increasing. Okay, so these probabilities are increasing, but furthermore, they're jumping. Okay? At some point, some of these guys are jumping. So if Vi and Vi plus 1 were split from the same parent, there had to be a reason for that split. The collision probability was too high. And that means that they weren't close to uniform. If they're not close to uniform, then there has to be a reasonable difference between the smallest element in Vi and the largest element in Vi plus 1. Okay? So you can actually make this formal proof, a lemma that says that if Vi and Vi plus 1 were split, there's at least a 1 plus beta factor difference in the probabilities of the extreme elements. Okay? So you're either getting bigger or you're always getting bigger, but sometimes you're actually jumping up in probability weight. Okay? Well, there's not that far you can jump. Okay, so let me also mention that actually at least half of these guys have to be jumps. Okay, because this tree was full, at least half of these internal nodes have to be siblings. Okay, so at least half of 1 through m, half of these guys have to be siblings. So half of these had to be jumps. Okay, and you can't jump that far because you start at something that's at least 1 over log cubed n large, because we got rid of all those really small weight nodes. And a probability can't be bigger than 1. Okay? So how much can you jump? You can only jump log n times. Okay, so you can use this to bound the number of live intervals per row of that tree. Okay, this just in case you don't remember, this is the tree I'm talking about. So any row on this tree can have at most log n many nodes on it. Okay? And the depth is only log n. So the total number of nodes is at most log n, log n. Okay, and that's how you show that. All right, so what this gives you is an O tilde of n to the 1/2 over epsilon squared sample complexity bound for distinguishing monotone distributions from distributions that are epsilon far from monotone. Okay, what about general posets, not just totally ordered posets? Here the story gets a little bit more intricate and maybe good because there's lots of open questions. But it turns out that if your poset has nice properties like it's decomposable into a union of W disjoint chains of length at most C, then you can test distributions with O tilde of W root C many samples. Okay. So how do you do that? Well, you approximate each chain of the distribution of the poset by a k-flat distribution, and then you check if the resulting distribution is close to monotone. But now you have to check that things are consistent between chains as well. Okay, but it turns out something that is doable. What's nice about this is that it gives an O tilde of capital N to the 3/2 bound for the capital N by capital N grid, which was actually roughly known before, but this simplifies greatly and is slightly more efficient than a result that was known before. And it also gives a slightly sublinear bound for the hypercube. Okay? So the capital N dimensional hypercube has 2 to the n many nodes, but you can actually test monotonicity in 2 to the n over root capital N. Many samples on the hypercube. So it's sort of a general purpose result. It's possible you can do better on that hypercube, I don't know. It's also possible that you can do better on the capital N by n grid. Okay, now the bad news is there are also posets, actually very simple posets, just the matching, for which monotonicity testing requires nearly linear samples. So that's kind of depressing because previously all these examples of problems where we knew we needed nearly linear samples were these kind of distance approximation problems, and we were kind of hoping that would, we could stop the damage there. But here is a real property testing problem where even that requires nearly linear samples. Okay, well, Okay, so let me just, this is my slide to pretend that there are other properties of shape that I'm interested in. One is cheating because it's unimodal distributions, which is essentially monotone and then anti-monotone part. One might also be interested in clusterable distributions. Is the support of the distribution k clusterable by radius r? So it turns out that that's something that you can say. Something that's actually open, but I would imagine that if anybody thought about it, you could do something about this, is what about testing whether a distribution is k-flat? Okay? So the techniques I mentioned work only when you start with something monotone, when you're testing so the techniques I mentioned, if you start with a k-flat distribution, may not actually output a k-flat representation. So it's not clear that the techniques I mentioned actually give you anything for testing whether a distribution is representable by a k-flat distribution or not. But what they may be able to do is approximate the best k. Okay, so that's still open. And something that I think people would be interested in is if you could test whether your distribution is a mixture of k-Gaussians, especially if you could do this faster than it takes to actually learn the k-Gaussians. Okay, so there's a lot of literature on learning mixtures of k-Gaussians. But what about testing? And maybe if you could do it sublinear in k, that would be even more amazing. Okay, so now I want to stop talking about testing properties of shape. I want to talk about how you can use the shape of the distribution to help you test other properties. Okay, so here's an example. If you have a distribution that's uniform on any subset of the elements, okay, not necessarily even contiguous subset of the elements, in this case, you can estimate the entropy somewhat faster than you could if you didn't know anything about the distribution. Okay, so that's one example. What if you know that your distribution is monotone? And let's start with totally ordered domains. Okay, if you know your distribution is monotone, how about testing uniformity? Remember before, when you knew nothing about your distribution, we needed root n samples. How many do you need now? Constant. Okay, really 1 over epsilon, but I mean 1 over polynomial in epsilon. But constant in terms of the domain size. That's all you need. Because if you know the distribution is monotone, all you need to do is make sure that the distribution assigns roughly the same amount to the left half of the domain as it does to the right half. Okay? And you can show that the difference in weights it assigns to the two halves of the distribution ties directly into its distance from uniform. Okay, so you can prove that kind of relationship. It's simple algebra. And you're done. Okay? Something else you can do when you know your distribution is monotone over a totally ordered domain is, with polylogarithmically many samples, you can test closeness, you can test independence, you can estimate the entropy. These are all things that took n to the 1/2, n to the 2/3, n to the 1 over gamma for gamma greater than 1. Many samples when you didn't know anything about the distribution, but now you can do it with polylogarithmically many samples. And the idea you might actually guess by now is to use these k-flat partitions to approximate the distributions. But now since you know it's monotone, you don't have to do that uniformity testing step everywhere. You can just figure out the partition, and you don't have to check the collisions in between. Okay? So you figure out how to partition it with a slightly different criteria, but essentially the same idea. And once you figure out a k-flat approximation of your distribution, you can just test the property on the approximation, and you're done. Okay? So monotone, knowing that the distribution is monotone helps you an awful lot for testing these properties. Okay, what about partially ordered domains? Can we get the same big wins in that case as well? Okay, well, let's take an example of a partially ordered domain that has high dimension, the most high dimension. Let's take the Boolean cube. Okay, so 0, 1 to the n. This is our biggest point, 1 to the n. That's our lowest point, 0 to the n. And we want to know here, can we get algorithms whose sample complexity is polylogarithmic in the domain size for testing uniformity, testing identity, entropy? And remember here, polylogarithmic in the domain size, which is 2 to the capital N, is the same as saying it's polynomial in capital N. Okay? Okay, so I'm using capital N for the dimension. And it turns out that there's some good news. Testing uniformity can be done in O tilde of capital N, the dimension, over epsilon squared sample complexity. Okay, so for testing uniformity, and how do you do this? Well, to say this, let me define something called the bias. Bias of a domain element x, okay, this has nothing to do with the probability distribution, it's just the bias of a string x. It's 2 times the number of 1s in x minus capital N. So the top element has bias n, the bottom element has bias minus n, the equator has bias 0, and the bias essentially tells you which level of this hypercube you're on. Okay, that's all it tells you, and just it's normalized to minus n and capital N. Okay, so notice that for the uniform distribution, if the expectation over x chosen from the uniform distribution of the bias of x, in other words, the average bias of x, is just 0. Okay, that's pretty easy to see. If p is monotone, it's also fairly straightforward to see that the expected bias is positive. Okay? If it's not the uniform distribution, then it has to be top-heavy. Okay, so it has to be positive. All right, so we're going to use this. Okay, so let's think now. We've defined this thing of bias. The uniform distribution has bias 0. Okay, we know our distribution is monotone, so we know our bias is positive. The only monotone distribution that has bias 0 is the uniform distribution. Okay, so how about to test for uniformity? Okay, we know P is monotone. We're testing for uniformity. How about we do this? Why don't we just estimate the bias and see if it's close to 0? Okay, and that, in fact, is going to be our algorithm. We're going to take a bunch of samples, calculate the average bias, and if the bias is close to 0, let's say less than epsilon over 2, we're going to output uniform. If it's greater than epsilon over 2, then we have significant bias, so then it couldn't have been the uniform distribution, and we'll output not uniform. Okay, so that's going to be the algorithm. And it's pretty clear if this, okay, so I'm showing you actually a first try. So this is more samples than what I originally claimed. This particular algorithm takes capital N squared many samples. But with that many samples, if you plug it into your Hufting bounds, you get a really good estimate of the bias. Okay? And then if you plugged in the uniform, if you took samples from the uniform distribution and you took that many samples of it, you're going to get a good estimate of 0 to within epsilon over 2. Okay, so you really are going to see a number that's less than epsilon over 2. And, okay, so the only question that remains here is, why is it that step 2 catches non-uniform distributions? Okay, why is it that non-uniform distributions are usually going to output far from uniform? So it has to be, what we have to show is that their bias is at least epsilon, that their expected bias is at least epsilon. Okay, so that's what we're going to show next, that their expected bias is at least epsilon. And then, because of the good sampling, like because we took enough samples that we can apply Hufting bounds, we're going to, if our expected bias is at least epsilon, so our estimator is going to be at least epsilon over 2 with high probability. Okay? So that's what we need to do now, is show that the expected bias is at least epsilon in the case that the P was at least epsilon far from uniform. Okay? Now, I'm not going to prove this, but I'm just going to say a few words about the proof. It follows from a canonical path argument, and it can be viewed as a real-valued version of the classic result that any balanced monotone partition of the hypercube into red and blue nodes has to have at least omega 2 to the n bichromatic edges. So it's a sort of influence-type argument. Okay? All right. To give the more efficient version of this result, you just have to slightly modify the algorithm. Let me just go back to this picture. So to slightly modify this algorithm, notice that for the uniform distribution, if you take that many samples, you expect them actually all to be within a root n, square root n band around the midpoint here. Okay, it's very unlikely. Okay, go ahead. Okay, it's very unlikely you'll be way up here or way down here. So they're actually, you expect them all to be here. So why don't we say that if we see anything up here, just reject. This couldn't have been the uniform distribution. Okay? Why does that help? What it helped is that it changes the value of our, it lowers the variance. Okay, so it gives us a range of O tilde of n to the 1/2 rather than a range of O of capital N. And so we can plug in better numbers into our Hufting bounds, and it gives us a sample complexity of O tilde of n rather than O tilde of n squared. Okay, so that's just how you can improve that algorithm. Okay, so we just saw a positive result. We can test monotone distributions for uniformity using O tilde of the dimension many samples, but unfortunately for all these other problems, things are not so great. Okay, so it turns out that you can show an exponential in the dimension lower bound for testing equivalence to a known distribution, or what I also called testing identity earlier. Okay, so, and the really depressing thing is, it's even for just the simplest possible known distribution, a product distribution. You would think that if you could test uniformity quickly, you should be able to test a product distribution because it's so similar to a uniform distribution. It's independent, every bit is set to 1 with even probability 2/3. Even that, we can't, there's an exponential lower bound. Okay? So that's kind of depressing. And there's also an exponential in the dimension lower bound for approximating entropy. And it turns out that there's a technique that's based on monotone subcube decomposition. You can use these to define a class of distributions to give all these lower bounds. So it's the same technique for all of these. You can also show that this uniformity test is nearly the best possible. So you need some dependence. You need a linear dependence on the dimension, which means that you can't be completely independent of the domain size in this testing problems. Okay, so this is kind of depressing, but it still leaves open the possibility that you can do better knowing that the distribution is monotone than the results we have for when you don't know anything at all about the distribution. So remember there we had, for testing equivalence to a known distribution, we needed root the domain size many samples. That would be 2 to the capital N over 2. Okay? So it may be possible, knowing that the distribution is monotone, to test it with 2 to the capital N over 10 or something like that. Okay? So that's a possibility. Also open is other kinds of partial orders. And I guess at this point, I hope I've convinced you that there are a lot of open problems in this area. There's several useful techniques known. We borrowed from learning theory, from influence of Boolean functions. Some of it is just algebraic calculations. But there's a lot of different directions to go. I think the main open questions are what other properties have sublinear tests for them? And when we have strong lower bounds, are there some kind of reasonable assumptions we can make on the distributions so that we can get better algorithms for them? Another thing that I didn't talk about at all is what about other query models? For example, I assumed here that you could not access probabilities of the distributions. I could not ask what's the probability of element 10. Okay? But actually, it may be reasonable in some cases to assume you have that kind of access. For example, Google, a couple of years ago, made public a bunch of texts it had collected and all the n-gram data. So they did all those calculations for you, and then you spend 2 days downloading this huge data set. But then you have all the texts which you can randomly sample, so you can construct your own little routine that gets a random sample of a text. And you can also query their statistics to see the probability of every single word and also the probability of co-locations of words. So there's a lot of information that they did for you. And you could do yourself if you had a lot of pre-processing time. So I think that this question of other query models can be an interesting one. One just has to find the right setting. And one other one I'll just throw out there is what happens when you can't assume that your samples are IID, but maybe you can assume some other relationship between them. Okay, so that's it.